All right, everybody, grab your clipboards, lace up those field boots, and welcome to the great outdoors. I am just so incredibly thrilled to be your guide for today's Field Practicum Explainer. Today, we're totally ditching the dusty textbooks. Instead, we're actually going to learn how to translate raw, muddy earth into perfectly precise maps. We're getting right into the beautiful, dirt under the fingernails groundwork of basic surveying techniques. So let's dive right in. Here's a quick mental syllabus for today's practicum. We'll start with Welcome to the Field, then move on to Mastering Chain Surveying, Mapping with Offsets, the Plane Table Method, and finally, Surviving Surveying Errors. Section 1. Welcome to the Field, Demystifying the Oldest Surveying Methods. Okay, our very first technique is wonderfully simple. I'm talking about chain surveying, which is literally the oldest method of land surveying out there. And why is it so enduring? Well, because you are only making linear measurements. We are talking straight lines using a physical chain or a tape measure. There are zero angular measurements involved here. No complicated calculations for angles, no heavy optical equipment to measure degrees. You just lay your chain down on an open, flat piece of ground and you measure the distance. It's brilliantly straightforward and it's absolutely perfect for smaller areas. Section 2. Mastering Chain Surveying, Building the Skeletal Framework. Now, you might think a chain is just a chain, right? But in surveying, every chain has a very specific pedigree. First up, we have Gunter's chain. This one comes in at exactly 66 feet and is made up of 100 links. It's an absolute classic, and honestly, it's still brilliant for measuring land in acres. Then you've got the engineer's chain, which is a nice, clean 100 feet long. But the real modern hero of our practicum is the metric chain, usually 20 or 30 meters long, and that's the one you'll see used most widely today. And finally, there's the highly specialized 33-foot revenue chain, which was historically used for cadastral and land revenue work. So, depending on the job, you pull the right chain from the truck. So the big question is, how do we actually use these chains to make a map? And that brings us to the absolute golden rule of chain surveying. To map an area using only straight lines, we must divide our land into a network of well-conditioned triangles. And by well-conditioned, I mean no angle in that triangle should be less than 30 degrees or greater than 120 degrees. Now, why triangles? Well, think about it. A triangle is literally the only geometric figure that is uniquely determined just by measuring its three sides. If you measure those three sides, that triangle is locked in. It can't shift. By chaining these perfect triangles together, we create this unshakable skeletal framework across our entire site. Section 3. Mapping with Offsets, Locating the Beautiful Details. Once we have that skeleton, we want to capture all those beautiful little details around us: trees, building corners, fences. To do that, we use offsets. An offset is just a lateral distance measured from our main survey line to an object. And we basically have two choices here. Perpendicular offsets are the gold standard. We measure at an exact 90-degree angle from our chain line directly out to the object. It's highly accurate, especially for anything within about 15 meters, but, sometimes nature just doesn't cooperate. Maybe there's a giant thorny bush directly in the way of your 90-degree line. That is exactly when we use oblique offsets, which are measured at angles other than 90 degrees. They're slightly less accurate since you have to measure from two different stations on the chain line to pinpoint the object, but man, they are a total lifesaver when the terrain gets stubborn. Now, to get those perfect 90-degree perpendicular offsets, we rely on a couple of really trusty tools. Let's compare them. First, we have the basic crossstaff. It features these simple visual vanes set right at 90 degrees. You literally just look through the slits, line up your target, and boom, you've got a right angle. It's fantastic for flat ground, but if you want maximum precision, you're going to reach for the optical square. This little beauty uses two internal mirrors set exactly at 45 degrees. When you look into it, the object and its reflection magically align only when you are at a perfect 90-degree angle to your survey line. It is a massive upgrade for setting super accurate perpendicular lines. Okay, so how do we write all this down without completely losing our minds? We use a fieldbook and it comes with a delightfully quirky set of rules. Step 1, you actually start writing at the very bottom of the page. I know, it feels totally backward, but just trust me on this. Step 2, you record your main chainages, so your distances along that central survey line, straight up the middle column of the page. Step 3, if a tree is off to the left of your line, in the real world, you sketch its offset on the left side of the page. If a building is on the right, it goes on the right. Simple. Step 4, you work your way upward toward the top of the page as you walk forward in the field. This way, your notebook precisely mimics your physical forward movement on the ground. Section 4, the Plane Table Method, live streaming the terrain onto paper. I have to admit, plane table surveying is my absolute favorite. It is honestly sheer magic. It's what we call a graphical method of surveying. That means your field observations and your actual map drawing happen simultaneously, right there on the site. You literally attach a piece of drawing paper to a flat wooden board on a tripod, stand out in the field, and draw the map as you look at the terrain. No field book is required, and you completely eliminate the need to go back to some dusty office later to do separate math calculations. Plus, you can instantly visually compare the map you're drawing with the actual site right in front of you. And here is the absolute beating heart of this technique. The rule is, all rays drawn through various details should pass through the survey station. This is the core principle of parallelism, and it's just beautiful. It basically means that every single line you draw on your paper is perfectly parallel to the real-world direction you are gazing at out in the field. So when you sight a distant building and draw down your ruler, that pencil line is geometrically parallel to your actual line of sight. Let's quickly look at the gear that makes this parallelism possible. Here's your essential accessory list. First, you've got the plane table and tripod. That's your stable base. Next is the alidade. This is your sighting device. Think of it as basically a fancy ruler with sight vanes that you use to draw those parallel lines. Then you need the trough compass to find magnetic north so your board is always oriented correctly. You'll absolutely need a spirit level to ensure your drawing board is perfectly horizontal because otherwise your distances will warp. And finally, the plumbing fork and plumb bob, which let you perfectly center the exact point on your paper directly over the physical peg in the ground beneath you. Section 5. Surviving Surveying Errors, Nature, Broken Tools, and Clumsy Hands. Now, as your practicum professor, I do have to warn you. Nature, broken tools, and our own clumsy human hands are constantly conspiring to ruin our gorgeous maps. Whenever you're out in the field, errors are gonna creep in. Let's break down the 3 main culprits. First, instrumental errors. Maybe your measuring chain is physically stretched out from years of use, or your alidade's edge isn't perfectly straight anymore. In that case, blame the gear. Second, personal errors. Now this one is entirely on you, like misreading the tape measure or having a shaky hand while drawing your rays on the plane table. Third, natural or plotting errors. This is the environment messing with you. Wind blowing your tape out of a straight line, trying to measure on a steep slope, or even the ambient moisture in the air causing your plane table paper to shrink and warp. It's really crucial to understand that not all errors are created equal. We classify them into 2 main types. First, we have cumulative errors. These are the highly dangerous ones. They happen in the same direction constantly. For example, if your measuring chain is 2 inches too short, every single time you lay it down, you are adding 2 inches of error. They silently accumulate over time and are the absolute most serious threat to the accuracy of your map. On the other hand, we have compensating errors. These occur randomly in both positive and negative directions, like sometimes guessing slightly over a mark and sometimes slightly under. Because they're completely random, they actually tend to sort of magically cancel each other out over a long distance. So yeah, it's those cumulative errors you really have to watch out for. Well, as we wrap up today's Practicum Explainer and start packing up our chains and our plane tables, I want to leave you with this provocative thought. Knowing the immense physical labor, the strict geometry, and the incredibly clever analog tools required to map the Earth by hand, how will this change the way you view that digital map sitting so conveniently on your phone? Remember, every single digital line on that screen was once walked, chained, and sighted by someone with dirt under their boots. All right, class dismissed. Keep exploring, and I'll see you in the next explainer.